Hello everyone, welcome to Marketing Research, MKTG 457, and this is chapter 15. In chapter 15, let's talk about how do you test for differences between groups and for predictive relationships. Okay? After studying this chapter, you should be able to choose an appropriate statistics based on data characteristics. Okay? Compute a chi-square statistic for crosstab results. Use t-test to compare a difference between two means, t-test, and conduct a one-way analysis of variance test. One-way analysis of variance test called ANOVA, and appreciate the practicality of modern statistical software packages. Okay? Understand the general linear model. The general linear model can predict the key dependent variable. Okay? A surprising number of inferences involve two variables. You can use the two variables, study two variables to find a lot of relationships. Okay? The automated search for relationship between the two variables provides the backbone for automated big data searchers. Okay? Sometimes the marketing analyst reduces a more complex analysis involving multiple variables to a series of two variable comparison because presenting the results becomes very simple. Okay? So it's easier to understand, easier to visualize, easier to comprehend, and easier to apply to other scenarios. Okay? So what is the appropriate test statistic? Okay? What kind of statistics tools do you want to use? Right? Researchers commonly test hypotheses stating that two groups differ. Right? Two groups differ. For example, men and women are different, with regard to certain things they do or believe, right? And the heavy user product versus the light user product, they may have different characteristics, etc. Right? Such tests are bivariate tests of differences when they involve only two variables. You have two variables because of bivariate tests of differences. Both the type of measurement and the number of groups to be compared influence the type of bivariate statistical analysis. So what type of measurement is involved, and also the number of groups involved, right? Determine what type of bivariate statistical tools you can use. Okay? So what is the appropriate test statistics? Right? Two questions help determine the analytical approach you have. Right? First, how many independent variables, IV, and dependent variables, DV, are involved in the analysis? How many IV and how many DVs? Okay? What is the skill level of the independent and dependent variables involved? The skill level measurement that we talked about before. Okay? This is a good summary table showing the right statistic to choose to conduct your test. Okay? If the independent variable, the x, this here is the dependent variable, the y, and normally use y. Okay? If you have one nominal or ordinal independent variable, okay, and you have one nominal or ordinal dependent variable, you can use a cross tabulation with chi-square test. Okay, if you have two or more nominal variables, you can use cross tabulation with chi-square test here. Okay, if you have one at least interval dependent variable with one nominal ordinal independent variable, you can do a t-test or one-way ANOVA, or t-test one-way ANOVA or n-way ANOVA. Okay. If you have more than one dependent variables, you can do multivariate analysis or multivariate ANOVA. Okay. If you have at least one nominal ordinal independent variables and at least one interval or ratio independent variables, you can do multivariate analysis. You have just one nominal dependent variables or logistic regression. And then you have one at least interval dependent variable, you can do full factorial ANCOVA, right? ANCOVA. And then you can have, if you have more than one dependent variable, you can do multivariate Markova. Okay? If you have one interval or ratio IV and one nominal ordinal DV, you can do a t-test. Okay? You have one at least interval DV, you can do a simple regression. Okay? If you have one or more interval ratio independent variables and one nominal DV, you can do multivariate analysis. That's logistic regressions, right? Logistic regressions. And if you have at least one interval, at least the interval dependent variable, you can do multiple regressions. Okay. Basically, for the scope of this class, you know, I don't expect you to do all of them, to use all of them. I want you to use the ones in the middle here, the light blue one. Or more specifically, I want you to do this, right? You're going to do a t-test and a one-way ANOVA. I expect you to do this. And also, I need you to do a simple regression and t-test and the chi-square test. Okay. Let me say it again. I'm expecting you to be able to do a cross-tab with a chi-square test, a t-test, simple regression, and one-way ANOVA. Okay, one-way ANOVA. And the others, you know, it just is now required for you to do in your group project. Okay, but this table can serve as a good guideline for you to determine what kind of analysis is possible with the nature of dependent variables and independent variables. Okay. Crosstab tables, chi-square test for goodness of fit, right? One of the most widely used and simplest techniques for describing sets of relationship is a cross-tabulation. Okay? A crosstab, or what you also call contingency table, is a joint frequency distribution of observations on two or more nominal or ordinal variables. Okay, two or more nominal or ordinal variables. Okay, the chi-square distribution provides a means for testing the statistical significance of contingency tables. Okay. We don't need to go into the rationale or the math, the theory behind this chi-square distribution. I just need you to be able to use that. Use chi-square distribution when you test for the goodness of fit. Okay. The test involves comparing the observed frequencies, or O, with the expected frequency on each cell of the table. Okay. Observed frequency O, expected frequency is E. Okay. The chi-square test goodness of fit, right? The goodness or closeness of fit, right, of observed distribution with the expected distribution is captured by this statistic. Okay, the observed one versus expected one, okay, is captured with this statistic. The test allows us to conduct tests for significance in the analysis of the R times C contingency table. R is the number of rows you have, and C is the number of columns you have. So R, let's say 2 by 2. It's R is 2, C is 2, 2 rows and 2 columns. It'll be 2 by 2, okay, for example. Okay. The formula here is the E equals RC divided by N. What is R? Okay. The R here is the total observed frequency counted in the ith row, right? CH is the total observed frequency count in the jth column, and N is sample size, okay? And the E is the ratio, okay? And to do a chi-square test, okay, E is the expected value here. Okay? The chi-square is calculated by O minus E, right? And squared divided by E and summed up. That's your chi-square, right? The degrees freedom for that is R minus 1 times C minus 1. R is C as the number of rows, C is the number of columns. O is what is observed, E is what is expected. Okay, observed value versus expected value. This is how you calculate the chi-square. You calculate chi-square and you look at the standardized table, and you find that if the chi-square statistic is larger than the table or than stat or not, to determine if there is there's a difference or not. Okay, give example of chi-square test, right? Hypothetical, there is a, say, for example, on a cruise ship, right? On a cruise ship, the many travelers on the cruise ship, happily enjoying their time on the ocean, right? And then there's a salmonella outbreak, right? When the salmonella outbreak takes place, unfortunately, take a look at to see what happened, what is causing that, okay? And there is a retrospective cohort study conducted on that, okay? What they found is that all 300 people on cruise ships interviewed, 60 of them had symptoms consistent with salmonella, right? 60 of them had salmonella, right? And also questionnaires indicate that many of the case patients ate tomatoes from the salad bar on that day. Okay, many ate tomato on that, right? So the question here is, to study the exposure to tomatoes and the salmonella infection, right? If there's any connection here, okay? So the number of people who had salmonella versus not, right? And the number of people who had the tomatoes in the morning versus no tomatoes. What they found is that of the 300 people total, okay, they found 130 had tomatoes, 170 did not have tomatoes. And of the 300 people, 60 had salmonella, infected by salmonella, and 240 did not. Of that, 41 people, right, and had salmonella, caught salmonella infection, and also ate tomatoes, right? 19 had salmonella, but did not eat tomatoes. Now, and also for those people who did not have the infection, 89 had tomatoes, and 150 did not have tomatoes. Okay, that's the observation, the observed number. Okay, now the question is, can we speculate if the eating tomatoes that morning caused people to have salmonella? Okay, yeah. Okay, so we could do this as a chi-square test. We want to see if there is a statistical difference in the amount of illness between those who ate tomatoes, that's 41 out of 130, and those who did not, that's 19 out of 170. Then we can use the chi-square test to find out, okay, if there's a statistical significant difference. Okay. So how do we calculate chi-square? We call the expected value, right? Because expected value is using the equation we just had, right? 41 minus 26 squared, and divided by that, you get 8.7. Then there's a 2.2, 6.6, 1.7. Okay? Using that number, we calculate chi-square. That's 19.2. That's chi-square. Okay. That's 8.7 plus 2.2 plus 6.6 plus 1.7 give you a total of 19.2. Okay? That's the chi-square statistics for this test. Okay, and then we need to find out the degree of freedom here. degree of freedom is C minus 1 times R minus 1. C, of course, there are two columns, the 2 minus 1. Rows, we have 2 rows, 2 minus 1, then it's just 1. Okay. Then the chi-square is just at point chi-square at 505 significance or 95% confidence level is 3.841, and our chi-square statistic is 19.2, and 19.2 of course is much larger than the 3.841. Therefore, what's our conclusion? Yeah. The salmonella autoinfection and eating tomatoes, the two are indeed associated, related. So in other words, we can conclude that the tomatoes probably did, a 95% confidence level did in fact cause the salmonella outbreak. Okay? Also, we can do a t-test for comparing two means, right? Independent sample t-test. A t-test is appropriate when a researcher needs to compare means for a variable grouped into two categories based on some less than interval variable. Less than interval variables between two categories, we will compare them, we can do a t-test. Okay. One way to think about this is testing the way dichotomous, the two levels, dichotomous independent variable is associated with changes in a continuous dependent variable between, for example, male and female, right? Young and old, or any other, variables. That's independent variables, just dichotomous, okay? Most typically, the researcher will apply the independent sample t-test, which tests the difference between the means taken from two independent sample or groups. And you take that and the t-test. The test assumes the two samples are drawn from normal distribution and that the variances of two populations are approximately equal. We're assuming that. That's our assumption here. They are drawn from a normal distribution, okay, the normal distribution, and the variance are approximately, the same. We call it the homoscedasticity, okay? Homoscedasticity, the equal variance assumption. Okay? The t-test usually actually tests whether or not the difference between the two means is zero. The difference between the two means is zero, meaning they are the same, they're not different, right? If the difference between the two means is not zero, then we're saying there is a difference. Okay, so the null hypothesis here is that mu1 equals mu2, or mu1 minus mu2 is zero, the same way. Okay? However, since this is the inferential statistic, we test the idea by comparing two sample means. We don't have the population means, right? We have sample means x1 and x2. We want you test the x1 bar minus x2 bar. That's sample, the mean of samples. Thus, the t-value is a ratio with information about the difference between the means provided by the sample in the numerator and the standard error in the denominator. That's the t-value. We call it t-value. The question is whether the observed difference, to take place by chance alone or not. Okay. Practically speaking, in practice, the computer software used to interpretation of the t-test is made by focusing on either the p-value or confidence interval in the group means. Right? Basically we use p-values. Right? When the p-value is close to 0, we say that there's a significant difference in the test is showing. Right? If a p-value is larger than, say, 0.01 or 0.05, depending on your confidence level you choose. If you choose confidence levels in 95, then we want to see if it's larger than 0.05. Right? If you want to choose confidence interval level of 99%, then we want to see if the p-value is larger than 0.01. Right? So So the basic steps here is you examine in the difference in means to find the direction of any difference, and then you compute or locate the computed t-test value, and then you find the p-value associated with this t and the corresponding degree of freedom. Okay. Note that the means may be the same due to the variance. So the test t statistics is a function of the standard error, so which is a function of standard deviation. Okay. You need to check for the outliers. You consider increasing the sample size and test again. And when the samples get larger, the t-test and z-test will tend to yield the same result. When the sample gets larger and larger. Okay. A t-test can be used with large samples. Okay. Data can be used with large samples. A z-test should not be used with small samples. You cannot use a z-test with small samples. Okay. A z-test can be used in instances where the population variance is known ahead of time. Okay, ahead of time. Okay. So this is the independent sample t-test results. Yeah. What are we looking at here? Okay. See here, it shows that the equal variance assumed, equal variance not assumed. Okay. And it shows the price, price they pay between Catholic and Protestant, right? The 57 Catholic consumers, then Protestant 43 of them. That's their mean. Okay? The standard deviation, the standard error. Okay, and the t-test statistic here in this case is 0.998. Okay, and the degree of freedom is 98. Okay? And the two-tailed significant level is 0.321. Right? The mean difference is here, the standard error is here. Okay? The computed t-test value shown in this column here, 29998. Okay? The p-value for t and the associated degree of freedom is 0.321, and it's much larger than the 0.05. Therefore, the conclusion is that there is no difference. There's no difference between what the Catholics paid versus Protestant consumers paid. Okay. Okay, this is an example here. You can study further in the textbook. Okay. Pair sample t-test. A pair sample t-test is appropriate when means that need to be compared are not from independent samples. For example, that is, the same respondent is measured twice. Your same respondent is measured twice. That means there's no need to be compared. We can use paired t-test when means that need to be compared are not from independent samples. Because they're dependent on each other. Okay. When a paired sample t-test is appropriate, the two numbers being compared are usually scored as separate variables. Okay. This is an example showing the paired t-test results. Okay. And here is showing the two group of people, satisfaction before and after ride, that they went to a joy ride in a theme park, for example, right? And the satisfaction level here, average satisfaction or satisfaction afterwards, before and after. Okay? The average difference between the means is here, mean difference. Right? Satisfaction 1 is 3.95. Satisfied that's 2, and 1 is 4.35. So before they are a little more satisfied, but after a little bit less satisfied. But are they different? They're from the same group of people, but are they different, right? And the T ratio here is minus 4.797, okay? And this probability level is significant, and they're showing that there is significance here. So indeed, it means that the people are not as satisfied after the right. So unfortunately, okay. The z-test, when you compare two proportions, if you need to compare two proportions, you should use the z-test. Z-test for differences of proportion is used to test hypothesis that two proportions will be significantly different for two independent samples or groups. Okay, this requires a sample size greater than 30. Okay, it is appropriate for hypothesis of this form. You can use a pi for proportions. Pi 1 equal to null hypothesis here is the pi 1 does not equal to pi 2, or pi 1 minus pi 2 equals 0. Okay, that's a null hypothesis. Okay. The comparison of the observed sample proportions P1 and P2 allows researchers to ask whether the difference from the two large random samples occur due to chance alone. Okay. The z-test formula for the proportion is that this P1 minus P2, pi 1 minus pi 2. Okay. P is a sample proportion in group 1. P2 is sample proportion in group 2. Okay. And pi 1 minus pi 2 is hypothesized population proportion 1 minus hypothesized population proportion 2. Okay. You just need to understand this. I'm not asking, requiring you to use that, to do that in your paper. Okay. The statistic works on the assumption that the value of pi 1 minus pi 2 is 0, meaning there's no difference there. Okay. Note that the similarity between this and the paired comparisons that we talked about before. Okay. Standard error of differences in proportions. This is the formula for standard error. Okay. Okay. And to calculate pooled estimate, you get this. Okay. That one, you just need to have a cursory knowledge of that, you'll be okay. Yeah. But I want you to focus on where you do use ANOVA here. Okay, ANOVA, right? When the means of more than two groups or populations are to be compared, one-way analysis of variance is the appropriate statistical tools. Okay? Basically, you want to compare more than two groups, say 3 groups, 4 groups, 5 groups. Okay. Say you have something like measurement about the attitudinal numbers or purchase intentions among different groups. Let's say between 4 different age groups or 5 different income levels. Okay, you want to compare that to more than 2 groups. You want to compare them in one at the same time. You can use ANOVA. I expect you to use ANOVA in your group project. I need you to identify one dependent variable that can be interval scaled, ratio scaled. I want you to identify, compare the means across more than the 2 categories, maybe 3 categories, 4 or 5, 3, 4, or 5 groups. You can choose any group you want. You can choose, say, income groups, right? Different groups of income, or different age groups. You can't do gender because there are only 2. Okay, so that's what I want you to do, right? So basically, when means of more than 2 groups or populations are to be compared, you can use ANOVA, one-way analysis of variance, ANOVA. Okay, ANOVA involving only one grouping variable is often referred to as one-way ANOVA. That's what we're going to do. You're going to be doing, because only one independent variable is involved. Okay. Another way to define ANOVA, the appropriate statistical technique to examine the effect of a less than interval independent variable on at least interval dependent variable. Okay. Simple illustration of ANOVA. Let's look at the example here. Yeah. Data given describing how much coffee respondents report drinking each day based on which shift they work. Excuse me. Let's say there are people, workers working for this factory. Okay? There are three shifts. Okay, day shift, night shift, and graveyard shift. Okay, the really late night shift. Okay, and they all drink coffees, right? But we want to see if the number of coffees consumed by, say, like a graveyard shift or night shift is more than, say, the day shift. Or in other words, if people are relying on coffee, the caffeine, to keep them awake during the night shift or graveyard shift. Okay, so when compare that, there's three groups to compare: day, night, graveyard. Okay, and the table displaying the means for each group and our mean is given here. And plots each observation with the bar and lines are corresponding to the variance. This is here. Okay, and this is the let's see. This is the mean for the day shift. This was the day shift. Okay, this number how many cups of coffee they have. Okay, and then this one is for the mean for the night shift. This is for the night shift. And the overall grand mean as well as the mean for the graveyard shift is here. Okay, does look like there is a difference among different shifts. Okay, looks like so, right? But we need to calculate to find out. The tool to use here, ANOVA. Okay, in ANOVA we partition the variance. Okay, we partition variance. Now, there is a total variability in the number of coffees consumed. And its implicit question with the user ANOVA is, how can the dependent variable best be predicted? How can we predict that? Right? How can that be predicted? By looking at the variability. Absent any additional information, the error in predicting an observation is minimized by choosing the central tendency or the mean of an interval variable that you can stand, right? And the total error or variability that would result from using the grand mean, meaning the mean over all observations, can be thought as like this. This SST, right, equals to, right, sum square of total, and sum square total equals total of observed value deviating from its grand mean, okay, and the squared. Okay, so although the term error is used, this really represents how much a total variation exists among the different groups. Okay, and we are looking at the between group variance versus within group variance. Okay, ANOVA tests whether the grouping observations explain variance in the different variables. The grouping, okay, observations explain the variance in different variables. If so, that means that there's a difference between the groups, right? The between group variance can be found by taking a total sum of weight difference between group means and the overall mean. Okay, so that's sum of squared between it equals to the group mean minus grand mean. Grand mean is above the total average mean, and squared. The weighting factor here is a specific group sample size. Okay? The total SSB sum of square between represents variation explained by the experimental or independent variables. In this case, is group. Okay. Then there's also the within group error, right? Within group error. Within each group, what the group means explain the variation between the total means and the group means. The distance from the group mean and each individual observation remains unexplained. And this distance is called the within group error or variance. Okay? The value for each observation can be found by SSE, sum square E error is total of observed mean divided minus its group mean. It's squared and summed up. Okay? That's SSE. The term total error variance, sum square total error, is sometimes used to refer to SSE since this variability not accounted for by the group means. Okay? So basically we look at the error or variance within group and between groups. Okay? This is a example, table showing how you're going to interpret the ANOVA data. Okay? In this case, we are looking at, let's see here, okay? The model, the intercept, and the mean squares, the F statistics, and the significance level. This row shows the overall F value testing whether all group means are equal. The sum square column calculates the SST, SSC, and SSB. Okay, this mean square total sum square, total sum of squares. Right, this is mean squares as mean square and F statistics. Right. For the model, the F statistics is 4.4. The significance is 0.039. Okay, so this shows the mean number of two cups for day shift, 4 cups for graveyard, and 6 cups for night shift. Okay, this is the standard error, the confidence interval. Okay, so the group means for each one. So what are we saying here? Okay? The intercept, the shift, right? The significance level is 0.039. So basically, we can now say there is a great significance difference among different ships, different groups, even though it looks like the night shift, and the graveyard shift drink more. Okay? Yeah. You can use Excel spreadsheet to calculate the ANOVA, and I want you to do that. Then I need to be able to explain the results, correctly. Okay. Okay. Let's see. Okay. F-test. ANOVA use F-test, right? F-test is a key statistical test for ANOVA model. Okay. It determines whether there is more variability in the score from one sample than in another sample. Okay. The key question here is whether the two samples variances are different from each other or whether they are from the same population. Okay. And the F statistics or F ratio can be obtained by taking the larger sample variance and divided by the smaller sample variance. Okay. And then we use a degree of freedom that need to be specified. Okay. We don't need to go. I don't need you to go to the fundamental math theories behind that. I just need to be able to use that F statistics, calculate F statistics, and make conclusion, based on that in your ANOVA test. Okay. The using variance components to compute the F ratios, there are 3 forms of variance. There's the SSE, there's the variance in the scores due to random error, sum of square error. There's SSB, the systematic variation between groups, the SSB between groups, and the SST, that's the total observed variation across all groups and individual observations. Okay, with grand means from individuals. Okay, that's SST. Okay. And F distribution is a function of ratio of these two, that's SSB over SSE. Okay. A larger ratio of variance between group to variance within group implies a greater value of F. Okay. The F is large, the results are likely to be statistically significant, meaning there is a difference among groups. Okay. Different but equivalent representation. F can also be thought of as a function of the between group variance and the total variance. Okay, you can express F like this: SSB divided by SST minus SSB. That is SSE, and the same thing. Okay. This example shows how to calculate the one-way ANOVA using SAS, GMP, SPSS, and Excel. This is GMP. We don't have that. Basically, all these tools are quite similar for myself, I have used SAS, I use SPSS and Excel. In this class, I need you to use Excel. Okay. Later on, I think I'll show you how to do Excel, analysis using ANOVA, using the statistical analytical analysis tool pack in Excel. That's provided there. Okay. This is Excel. Okay. I'll show you later on, or in my lectures. This is Excel. You can adding the analysis tool pack. You select ANOVA, enter the data, and then click OK. It'll calculate. Okay. And this is analysis tool pack here. Right. You can enter the range of data here. Right. Choose ANOVA, set your confidence level, and then here is the results, summary of the results of ANOVA. Okay. Yeah. Practically speaking, the first thing to check is whether or not the overall model F is significant. Okay. And second, the researcher must examine the actual means from each group to properly interpret the result. Okay. In statistical software, the marketing research analyst has access to statistical software that facilitates statistical analysis by quickly and easily providing results for t-test, crosstab, ANOVA, JLM, and more. Okay, can do that. Some data mining routines even automate some of this analysis. Some data mining routines. Okay. And some of the most common statistical software packages are SPSS, that's now is owned by IBM, and SAS, and a new user-friendly product called JMP, and then Excel, of course, is another one. Okay. Excel includes basic data analysis function and add-in data analysis function that contains procedures like ANOVA, or for marketing researchers, packages, excuse me, packages like SPSS and JMP offer an easy-to-use interface and a standardized approach to statistics. Basically, if you know how to use the one in Excel, you should be able to easily adapt to use SPS and JMP, which is more user-friendly. Okay. General linear model. Let's talk about general linear model. What is general linear model? Multivariate dependence techniques are variants of the general linear model. All those multivariate dependence techniques actually can be all, considered a variance of the general linear model. Okay? General linear model, or GLM, is a way of modeling some process based on how different variables cause fluctuations from the average dependent variable. Okay? Fluctuations can come in the form of group means that differ from the overall mean, as is in the case of ANOVA, or in the form of a significant slope coefficient, as in regression. Okay, I just need you to have some working knowledge of this, and then you'll be okay. Okay. The general linear model equation is this, right? The y expected value equals y bar plus the changes in x, changes in delta x, delta f, and delta xf. Okay. Here, y bar represents a constant, which can be thought of as the overall mean of a dependent variable or independent variable. Theta x and theta f represent the changes due to main effect independent variables, such as experimental variables, and blocking independent variables, such as covariate or group variables, respectively. And the delta xf represents the change due to the combination or interaction effect of those variables. That's why it's called a general linear model, and it kind of summarizes all. Okay. Yi is in this case could represent the multiple dependent variables, such as x, and f could represent multiple independent variables. Okay, so Yi in this case is the dependent variables, multiple dependent variables. Okay. ANOVA representation would add the continuous covariate x. Okay, that will be a novel representation using general linear model. So, regression analysis. Let's start with regression analysis. Regression analysis investigates the straight line relationship of the type y equals alpha plus beta x. I'm sure you in your algebra you studied, y plus a times b times x. Okay, we can use alpha and beta here in this case. Okay, y is continuous dependent variable, and x is an independent variable. That's usually continuous, although dichotomous, nominal or ordinal variables can be included in the form of dummy variable. That's fine. So normally say like y is a dependent variable. Say for example, it's purchase intention. Or let's take an example. Let's say y is your lifelong earning, somebody's lifelong earning, right? And x is a level of education. We know your lifelong earning is dependent on your level of education. That's why you're here for college degree. Okay? The more education you have, the more lifelong earning you can accumulate. Okay, that will be a simple regression model. Okay? Alpha and beta are the two parameters that must be estimated so that the equation best represents a given set of data. Okay, you can collect data to have a lot of people, a lot of observation in the data set, with everyone has income level, lifelong earning number, and also level of education, maybe education in years. Okay? These two parameters determine the height of the regression line and the angle of the line relative to horizontal lines. Okay? When these parameters change, the line changes as well. Okay? For multiple regression analysis, even though it's not required for you to do in this class, multiple regression analysis allows one dependent variable to be explained by more than one independent variable. Again, they have several independent variables. Okay, when trying to explain sales, for example, what are the possible causes of sales or factors that contributing to sales? Plausible independent variables may include the price of the products, economic factors, advertising intensity, and consumers' income in the area. Okay? So one dependent variable, sales, can be explained by several independent variables, and then we can use multiple regression to represent. Okay? A simple regression equation can be expanded to represent multiple regression analysis. We use the y here, that's the sales, b is a constant, then x1 may be the price, x2 may be economic factors, x3 advertising, blah blah blah. Okay, plus an error term. Okay. Parameter estimate choices. The estimates of alpha and beta are the key to regression analysis. We're speculating or we're anticipating a straight line relationship, linear relationship, right? Then what is intercept? What's the slope of the line? Then that is alpha and beta. Okay. In most business research, the estimate of beta is most important. The alpha is constant. We want to see the beta coefficient, right? The slope, right? The slope determines how fast, this to what degree this independent variable affects the dependent variable. For example, how much would an increase in advertising spending affecting the sales? Right? We want interest in the beta, okay? The slope. The explanatory power of regression rests with beta because this is where the direction and strength of the relationship between independent variable and dependent variable is explained. The direction, if it's a positive, there's a positive correlation, right? The one goes up, the other goes up. If it's negative, one goes up, the other goes down, right? The strength, the larger the variable, the stronger the relationship, okay? A y-intercept term is sometimes referred to as a constant because the alpha represents a fixed point, just the intercept. Okay? Estimate slope coefficient is sometimes referred to as a regression weight, regression coefficient, and sometimes even as a path estimate. Okay? Researchers often explain the regression results by referring to a standardized regression coefficient called beta. Okay? A standardized coefficient, regression coefficient like a correlation coefficient, provide a common metric allowing regression results to be compared to one another no matter what the original scale range may have been. Okay? Due to the mathematics involved in the standardization, the standard y-intercept term is always 0 if standardized. Okay. Examine the steps in interpreting a multiple regression model. Okay. You need to examine the model's f-test. Is the model f-test? If the result is not significant, the model should be dismissed. Okay. The f-test need to be significant. You examine the individual statistical tests for each parameter estimate. Okay. Independent variables with significant results can be considered as significant explanatory variable. You may look at economic factors, price, advertising, consumers, and maybe some of them are significant, some are not. Then you determine which one is significant. Okay. And also, you need to in interpreting multiple regression model, you need to look at the model's R-square. You examine R-square, right? There's no cutoff value exists that can distinguish an acceptable amount of explained variation across all regression models. R-squared represents the total variations explained by your model. That is your model's predicting power. If your model can explain a large portion of the total variance, you can say your model is pretty good. Can explain a lot of variations. Okay. There's no cutoff values, but normally if you have 0.3 or 0.4 or higher, that means your model can explain 30 to 40% of total variance. You can be pretty proud of yourself. Okay. The absolute value of R-squared is more important than the research when the researcher is more interested in the prediction than explanation. Excuse me. Excuse me. The next step would be to to diagnose multicollinearity. Because there's the extent to which the independent variables are redundant. This one shows. Excuse me. I'm going to drink some water. Sorry about that. This shows the steps in interpreting a multiple regression model. Okay, first you need the regression here, right? The sum of squares, the degree of freedom here, the mean squares. You mean square this divided by this, get you f statistic of 50.446. Now this is much larger than the table, than the abstract normal. And then the significance level is 0.000, meaning it's very significant. Okay? This model explains a significant portion of the variance in bonus in this study here. Okay? The dependent variables are bonus. The predictor variables are experience, hours, and tools, whatever that is. Okay? And then you need to look at R-squared. R-squared here is 0.477. That means that the model explains 47.7% of total variance in the dependent variable bonus. So that's pretty good. And 47, you can explain half of this, almost half of the variance. That's great, right? Here, you can look at individual parameter estimates, suggest that the hours, right? Hours significantly and positively influence bonus. This is hours, that's a positively, and also the t-value here, you see the significance. So hour is significant. the tools and experience are not. The meaning means that what affects bonus is hours or hours you worked, right? The tools and experience not that significant. That's how you explain the interpret the results. Okay. For your group project, I need you to identify one dependent variable. That could be whatever you are measuring, using Likert scale. Okay? And then I want you to identify several independent variables as to the factor that may affect a different variable. And then I need you to run the regression, multiple regression like this one. Right? And once you have a table like this, have data like this, I want you to explain the data. Okay, explain data. First, to see if the regression is significant by looking at the significance level here. The closer to zero, the better. Okay. If it's not significant, that's okay. But as long as you show me that you know how to do this, you're fine. You still can get a good score on your test on this project. Okay. And then you need to look at R squares, how much variance your model can explain. And then also look at each individual parameters, see which one is significant, which one is not. Okay, okay, that's all I have for this chapter. Sorry about my coughing. Yeah. Thank you. I will see you next time.